a cinematic meditation on the universe's hidden silence. Galaxies, colossal cities of stars, should be bound by gravity's eternal grip. Yet, as the cosmos expands, something unseen pries them apart. A mysterious energy fills the void, accelerating everything outward, as if space itself were being stretched by invisible hands. It is not light, not matter, not gravity, something stranger, darker, ungraspable. The narrator reflects on how humanity once believed the cosmos eternal, steady, unchanging until the discovery that it is driven by an unknown, silent force. A force that may define the fate of the universe itself. Welcome, you are watching Whisper Science. Make sure to subscribe and join us for more amazing science content. Now, let's move back to the video. In the early decades of the 20th century, the universe was imagined as a vast cathedral of stars, silent, eternal, and unchanging. Astronomers believed the cosmos was balanced, held in a steady state by the delicate tug of gravity. The heavens seemed fixed, as if the great dome of night were an unbroken mural. But science, like the stars themselves, moves restlessly. In the 1920s, a quiet revolution began atop Mount Wilson in California. There, a young astronomer named Edwin Hubble turned the 100-inch Hooker telescope toward faint smudges in the sky. These smudges, once thought to be mere gas clouds within the Milky Way, revealed themselves as entire galaxies, vast islands of suns drifting in the cosmic sea. Hubble measured the light of their stars, their redshifts stretched by motion, and made a discovery that shattered the illusion of a static universe. The galaxies were not still. They were fleeing from one another. Space itself was expanding. The idea was staggering. In the equations of Albert Einstein's general relativity, space and time were pliable, dynamic, alive with movement. Einstein himself had once introduced a term, the cosmological constant, to prevent collapse and to preserve a tranquil, eternal universe. But Hubble's evidence suggested the opposite. The cosmos was swelling, galaxies rushing outward, as if born from a single moment of fiery genesis. By mid-century, this expansion became the foundation of modern cosmology. The Big Bang replaced the static universe. Yet, within this acceptance lay an assumption. Gravity, the great binder of stars and planets, must surely act to slow the expansion. The universe would stretch, yes, but at a decreasing pace, the great dance of galaxies, held back by their mutual attraction. It was this expectation that guided astronomers for decades. The cosmos would expand, but like an arrow shot skyward, it would eventually yield to the pull of gravity, perhaps slowing towards stillness, perhaps collapsing in a grand reversal, the so-called Big Crunch. And then, in the late 20th century, another group of astronomers began asking a question both simple and profound. Was this slowing actually happening? To answer it, they turned to the universe's most reliable beacons, Type Ia supernova. These explosions, born from white dwarf stars consuming their companions until they reached a critical mass, blaze with almost uniform brilliance. They serve as cosmic mile markers, their light cutting across billions of light. By measuring their apparent brightness, astronomers could judge their distances with precision. By measuring their redshifts, they could trace the universe's expansion history. Two international teams formed, separated by continents, but united by curiosity. The Supernova Cosmology Project, led by Saul Perlmutter in California, and the High-Z Supernova Search Team, guided by Brian Schmidt and Adam Rees. For years they scanned the heavens, capturing the death throes of stars in distant galaxies, recording the faint whispers of cosmic history written in light. The process was painstaking. Vast stretches of sky were photographed, night after night. Images were compared, searching for faint points of light that had suddenly appeared, signs of a supernova blooming against the darkness. Once found, telescopes around the world raced to measure its spectrum, locking its redshift into record. And then the data began to gather. Supernova after supernova. Their distances calculated, their motions traced. The expectation was clear. The further away, the more the expansion should have slowed. The great story of gravity at work across billions of years. But the cosmos had prepared a revelation. The light told a different tale. These distant supernova were not just faint because of their vast distances. They were too faint. Their redshifts suggested they were further than expected. farther than any model of slowing expansion allowed. The conclusion was inescapable. The universe had not been decelerating at all. It had been accelerating. The silence of that realization shook cosmology. It was as though the universe itself whispered a truth no one had dared imagine. Some unseen force was pushing galaxies apart. Stronger than gravity, stronger than all the matter in existence. In 1998, both teams published their results almost simultaneously. Their findings aligned. The expansion of the universe was speeding up, propelled by something invisible, something scientists would call dark energy. The term was only a placeholder, a name for ignorance dressed as knowledge. But the data left no doubt. Nearly 70% of the universe was composed of this unknown entity, this silent force. In 2011, Perlmutter, Schmidt, and Rees would be awarded the Nobel Prize in Physics. Yet the prize was not for solving a mystery, but for opening one that remains unsolved. Their work revealed that the cosmos is not just stranger than imagined it, is stranger than imagination itself. The discovery phase of dark energy was not a moment of triumph, but of humility. The very fabric of the universe had shifted beneath human understanding. The age-old vision of a cosmos governed by light, matter, and gravity was incomplete. The galaxies were racing away, carried by a current that no one could see. A silent, invisible tide sweeping outward through eternity. And so, a new chapter of science began, with answers, but with a question vast enough to swallow everything once thought to be certain. What is the force that pulls galaxies apart? The universe had revealed a truth that seemed to defy reason. Expansion was not slowing. It was racing ahead, as if the very fabric of space were driven by a hidden wind. For centuries, gravity had been the trusted compass of the cosmos, binding stars to galaxies, galaxies to clusters, and clusters to the great web of cosmic structure. It was gravity that had shaped the Milky Way, birthed the sun, and held the Earth in its orbit. It was gravity that ruled the heavens. And yet here was evidence that gravity was not winning the cosmic battle. Something else stranger, quieter, and far more dominant was at play. The supernova data spoke with cold precision. Galaxies were not being reined in, but thrust apart faster and faster, as though an invisible repulsion were embedded within the very geometry of space-time. This was not merely a surprising discovery. It was a violation of expectation at the deepest level. For decades, cosmologists had accepted Einstein's general relativity as the grand framework of the universe. The theory predicted that expansion should decelerate under the pull of matter and energy. The only way for acceleration to exist was if there were a term in Einstein's equations to oppose gravity, a force that repelled instead of attracted. The irony was almost cruel. Einstein himself had once invented such a term, the cosmological constant, denoted by the symbol lambda. When he first formulated general relativity in 1915, his equations naturally described a dynamic universe either expanding or contracting, but at the time, no one could conceive of cosmic change. The prevailing wisdom, both scientific and philosophical, imagined the universe as eternal and static. To keep his equations aligned with this worldview, Einstein introduced lambda, a mathematical adjustment representing a uniform energy density filling space, counteracting gravity and holding the cosmos steady. When Hubble discovered expansion in the 1920s, Einstein abandoned the constant, calling it his greatest blunder. The term was thought unnecessary, a relic of an outdated idea. But now, nearly a century later, it returned with unsettling power. The acceleration discovered in 1998 suggested that the cosmological constant, or something very much like it, was real. Space itself contained energy, and that energy was pushing the universe apart. For physicists, this was not comforting symmetry, but alarming contradiction. Quantum field theory, the branch of physics describing particles and forces, had long predicted that empty space should contain vacuum energy, the restless fluctuations of quantum fields. But the predicted amount of this vacuum energy was colossal, more than 10 times greater than what was observed. A discrepancy so vast it was often called the worst theoretical prediction in the history of physics. Here was the shock. The cosmos demanded the existence of a mysterious energy. Quantum physics offered a candidate, yet the numbers were wrong by a scale so vast it mocked human calculation. Either quantum theory was incomplete, or some unknown principle was at work, canceling out almost all of the vacuum energy and leaving only a whisper of it behind. This was not simply an astronomical puzzle. It was a crisis of physics. For decades, scientists had spoken of theories of everything, frameworks that might unite the forces of nature, gravity, electromagnetism, the strong and weak nuclear interactions. The discovery of dark energy suggested that even if such a unification were achieved, it would remain inadequate. The majority of the universe as content as repulsive energy dominating space was not explained by any theory at all. The philosophical implications were staggering. Humanity had long believed that by studying matter, energy, and light, it could unravel the laws of existence. But now, more than 2/3 of the cosmos lay hidden behind a curtain of ignorance. Dark energy was not an anomaly at the edges of physics. It was the main stage. The familiar universe of atoms and stars was merely a small fraction of reality, a fragile island in an ocean of the unknown. The scientific community reeled. Cosmologists struggled to reconcile observation with theory. Some suggested that perhaps the data had been misread, that supernovae were dimmed by dust or altered by unknown processes. Others re-examined the cosmic microwave background, the faint afterglow of the Big Bang seeking corroboration. Yet every new observation confirmed the same story. Acceleration was real. Space itself, it seemed, was alive with a silent pressure. The very emptiness between galaxies was not empty at all, but suffused with an energy that could not be measured directly, only inferred from its effect on expansion. It was as though the universe were a stage lit by unseen spotlights. The galaxies were the actors, their motions visible. But behind them, in the unseen rafters, an invisible director moved the cosmos in ways the audience could barely perceive. The emotional weight of this realization was profound. For the first time since the dawn of science, humanity faced not just unknowns, but unknowables. If dark energy were a property of the vacuum, immutable and eternal, then perhaps it could never be manipulated. Never truly understood, only accepted as a fundamental truth, a cosmic background that defined existence itself. But if dark energy were dynamic, if it evolved with time, changed its strength, or interacted with matter, then the implications were even more unsettling. It could mean that the future of the universe is not fixed, but subject to transformations beyond prediction. It could mean that the laws of physics, as they appear today, are not eternal truths but temporary expressions of a deeper, hidden reality. For the astronomers who first glimpsed the faint light of distant supernova, the shock was not triumph, but vertigo. Their discovery had opened a chasm beneath the foundations of science. What was once thought to be stable ground, the balance of matter, energy, and gravity now seemed fragile, provisional, incomplete. The galaxies continued their silent flight outward, carried by a force beyond comprehension, and the scientists, left behind on their small blue planet, could do nothing but measure, calculate, and wonder. The universe had spoken in numbers, and those numbers revealed a truth stranger than dreams. Gravity was not supreme. A silent force ruled the cosmos, invisible yet overwhelming, rewriting the destiny of all things. Dark energy had arrived, not as an answer, but as a question so vast it threatened to undo the very idea of knowledge. The scientific shock was not just that the universe was accelerating. It was that humanity, after centuries of progress, had been reminded of its ignorance. The cosmos was not what it seemed. Perhaps it never had been. And so, physics entered a new era and age, not of mastery, but of humility. The universe had revealed its greatest secret, that most of itself was still a mystery. The shock of acceleration did not end with discovery. It was only the beginning. Once the supernova data declared its verdict, the scientific world turned its full attention to the enigma. If the cosmos was indeed accelerating, then every instrument, every telescope, every detector had to be summoned to examine the force driving it. The mystery demanded deeper investigation, and science began peeling back the layers of cosmic silence. The first task was confirmation. The faint light of type Ia supernova had carried the initial whisper of the truth, but whispers can be deceptive. Could these explosions have been dimmed by intervening dust, skewing the data? Could their uniform brilliance have been misunderstood? Teams across the globe set out to check, refine, and test. Soon, the universe provided its own corroboration, far beyond the reach of galaxies, woven into the very sky itself, lay the faint afterglow of creation, the cosmic microwave background. Discovered in 1965 by Arno Penzias and Robert Wilson. This radiation is the remnant firelight of the Big Bang, cooled and stretched across 13.8 billion years. It is a frozen record of the infant cosmos, a time when matter and light were still tightly coupled. Satellites like COBE, WMAP, and later the European Space Agency's Planck Observatory mapped this background in exquisite detail. What they revealed was astonishing. Faint ripples in temperature and density, patterns etched into the fabric of space, when it was only 380,000 years old. These ripples carried the fingerprints of the universe's composition. By comparing their distribution with the supernova data, scientists could measure not only how much matter the cosmos contained, but how much was missing. The answer was unsettlingly clear. Ordinary matter, the atoms that build stars, planets, oceans, and life, made up less than 5% of the universe. Dark matter, invisible yet gravitationally powerful, accounted for about a quarter, and the rest, the majority, was something else entirely. Something smooth, diffuse, and invisible, pervading all of space. The numbers matched the acceleration. Dark energy was not a fluke of supernova. It was embedded in the deepest cosmic record. Galaxies themselves provided further evidence. Astronomers began conducting vast redshift surveys, measuring the positions and motions of millions of galaxies across billions of light years. Projects like the Sloan Digital Sky Survey traced the great cosmic web, the filaments and voids of structure woven since the Big Bang. Within this tapestry lay subtle imprints, called baryon acoustic oscillations, faint echoes of primordial sound waves that rippled through the early plasma of the universe. These echoes acted like a standard ruler, allowing cosmologists to measure how the expansion had unfolded through time. The results aligned with the same unsettling truth. Expansion was not slowing, but accelerating. The silent hand of dark energy could be seen shaping galaxies themselves, influencing the very scaffolding of the cosmos. As more data poured in, the mystery grew sharper. Dark energy did not seem to cluster or clump. Unlike matter, it did not gather in galaxies or swirl in halos. It was smooth, uniform, everywhere, and yet, its influence was profound. Left unchecked, it would determine not only the present structure of the universe, but its ultimate fate. The investigation also revealed tension. Different methods of measuring the rate of expansion, the Hubble constant, did not agree. Supernova measurements and Kifid, variable stars, suggested one value. The cosmic microwave background suggested another. The discrepancy, now known as the Hubble tension, hinted that perhaps dark energy was not constant after all, but evolving through time. Or perhaps, even more radically, that our understanding of gravity itself was incomplete. Each new observation refined the boundaries of possibility. Was dark energy truly Einstein's cosmological constant, an intrinsic property of space itself? Or was it a dynamic field, like quintessence, evolving and shifting as the universe aged? If it were constant, the universe would continue accelerating forever, approaching a cold, empty heat death. If dynamic, the story could be stranger still. Acceleration might change, pause, or even reverse, leading to futures beyond imagination. To probe further, scientists needed sharper tools. New telescopes scanned the heavens with greater sensitivity. The Hubble Space Telescope, though built decades earlier, turned its eye toward supernova. So faint, they approached the edges of observability. The Very Large Telescope in Chile joined the effort, and soon, new projects like the Dark Energy Survey, the Dark Energy Spectroscopic Instrument, and the Euclid mission were designed specifically to unravel the mystery. Each layer of investigation brought both clarity and confusion. Clarity, in that every line of evidence confirmed acceleration. Confusion, in that none explained why. Dark energy remained untouched, unreachable, known only by its shadow on the motions of galaxies. Philosophically, the deepening of the mystery was unsettling. Humanity had always believed that with enough effort, the universe would yield its secrets. Yet here was a force that seemed woven into existence itself, offering no means of direct detection, no laboratory experiment to isolate it, The cosmos itself was the only experiment, and it was still running. Still, science pressed forward. Teams refined models, testing whether dark energy's density changed with time, whether it interacted with dark matter, whether it might decay or evolve. The data were precise, but the answers refused to settle. Like a horizon that recedes as one approaches, dark energy eluded final definition. And so, the deeper investigation revealed a paradox. The more that was learned, the less the universe seemed knowable. Every new instrument confirmed dark energy's presence, yet widened the gap between theory and observation. The cosmos was accelerating, yes, but the reason why remained cloaked in silence. Dark energy had become not just a phenomenon to study, but a mirror of human limitation. It forced scientists to confront the boundary of understanding, to ask whether some aspects of reality may forever remain beyond the reach of equations. Yet even within this humbling uncertainty, wonder grew. To live in an age when the universe, as deepest mystery, had only just been uncovered, was to stand at the threshold of something profound. For billions of years, galaxies had raced outward, driven by this hidden energy. For billions more, they will continue. And humanity, for a fleeting moment of cosmic time, has glimpsed the current that carries them. The deeper investigation did not solve the riddle. It revealed its immensity. A universe dominated not by matter or light, but by a silent force, vast and unseen. A force that shapes the fate of all things. And still, the question lingered, growing heavier with each new discovery. If dark energy is real, what is it? The universe had revealed its secret. Expansion was accelerating. Yet the deeper scientists peered into the mystery, the more unsettling it became. What began as a quiet anomaly in the light of distant supernova soon unfolded into a crisis that threatened the foundations of physics itself. The first escalation came with a simple realization. Acceleration was not just real, it was relentless. With every passing billion years, the universe would not merely stretch, but stretch faster. Galaxies already separated by millions of light-years would drift into unreachable isolation. The cosmic web itself would unravel strand by strand, leaving future observers marooned in islands of darkness. For them, the stars of other galaxies would vanish beyond the horizon, as though they had never existed. This picture of the far future was not mere speculation. It was written into the mathematics of expansion. If dark energy remained constant, the fabric of space would continue to accelerate forever. The universe would not collapse in a grand crunch, nor stabilize in eternal balance. It would dilute itself into silence and infinite, empty night where heat death awaited. But the equations allowed for even stranger fates. If dark energy were not constant but dynamic, its strength could grow with time. In such a scenario, known as phantom energy, the acceleration would become catastrophic. Galaxies would first be torn from one another. Then stars would drift apart. Then solar systems. Planets would be ripped from their orbits, atoms pulled apart, even the very structure of space-time shredded in a cataclysm called the Big Rip. A universe not simply fading, but violently unmade. The prospect was terrifying not for its immediacy, it lies billions of years in the future, but for what it implied. Dark energy was not merely a hidden presence. It was a power capable of deciding the fate of everything. From the largest clusters of galaxies to the smallest particles of matter. A silent hand not just pushing outward, but perhaps one day tearing reality apart. Even in the present, the mystery deepened through contradiction. As instruments improved, cosmologists tried to pin down the exact rate of expansion, but instead of convergence, they found conflict. Measurements from supernova and Cepheid variable stars gave one value. Measurements from the cosmic microwave background gave another. This discrepancy, known as the Hubble tension, became one of the great puzzles of modern science. Was it simply a matter of unseen errors in measurement? Or was it something more profound, a sign that dark energy itself evolves, that its influence changes across time? Some theorists suggested that we are witnessing the first hints of a new physics beyond Einstein, a breakdown of general relativity on cosmic scales. Others proposed that dark energy might interact with dark matter, exchanging influence in ways no telescope could directly record. Each attempt at explanation only widened the riddle. The universe seemed unwilling to resolve itself into clarity. It was as though dark energy shifted like a phantom, allowing itself to be measured but never understood, a constant presence whose essence slipped away whenever grasped. The escalation was not only scientific but philosophical. For centuries, humanity's search for knowledge had rested on the assumption that the universe was rational, comprehensible, governed by laws that could, at least in principle, be fully known. Dark energy mocked that assumption. Here was a force that dominated existence, yet remained invisible, untouchable, untestable in any earthly laboratory. It was known only through its absence, its effect on what could be seen. To call it energy was itself an act of desperation, a name given to ignorance. Perhaps it was not energy at all, but something deeper. An aspect of space-time so alien that human language could only circle around it without ever landing. Perhaps it was not even a single thing, but the shadow of phenomena existing beyond the observable universe. This deepening mystery forced cosmologists to confront questions once thought unscientific. Why does dark energy exist at all? Why is its strength so small, and yet so perfectly tuned that galaxies, stars, and life could emerge before it drove everything apart? If it were even slightly stronger, cosmic structure would never have formed. If weaker, the universe might already have collapsed. The coincidence seemed almost unbearable. Some invoked the anthropic principle. Perhaps there are many universes, each with different properties, and only in those where dark energy is finely balanced could observers like us arise. Others resisted this explanation, finding it unsatisfying, even unscientific, a surrender of the quest to truly understand. Yet the question lingered, unanswerable. Why this universe, with this strange and delicate balance? As if to heighten the tension, other anomalies appeared at the edges of data. Some galaxy surveys hinted at subtle patterns, not fully explained by standard cosmology. The distribution of matter, the clustering of galaxies, the flow of structures across the sky, all carried tiny deviations from expectation. None were definitive, but together they formed a chorus of doubt, whispering that something fundamental was missing. The escalation of mystery was like standing at the edge of a deep chasm. Every step forward brought not closure, but greater darkness. The more precisely scientists measured, the more impossible the answers became. The universe seemed to be teasing, revealing only fragments of the truth, retreating each time understanding drew near. For the public, dark energy became a phrase of wonder, a symbol of how little was known. For scientists, it became a wound-in open reminder that physics was incomplete. The Standard Model, the great achievement of the 20th century, could not account for it. Even general relativity, Einstein's masterpiece, could not explain why space should possess such a property. And so the escalation deepened into humility. Humanity, armed with satellites, telescopes, and equations, had touched the edges of the infinite, but the cosmos responded not with answers, but with silence. Dark energy was not just a scientific puzzle. It was a reminder of cosmic scale, of human smallness, of the profound gap between what is seen and what is real. Each new discovery, instead of closing the mystery, widened it, leaving only more profound and terrifying questions. And behind them all loomed the greatest question of all. If the universe is driven by a force so silent, so vast, so invisible, is reality itself built on foundations we may never reach? The silence of dark energy left scientists with no choice but to imagine. If galaxies were accelerating apart, if the universe itself was driven by a hidden pressure, then something must be responsible. Yet in the absence of direct evidence, only theories could fill the void. What emerged was not certainty, but a gallery of possibilities, profound, each incomplete, each reflecting humanity's attempt to name the unnameable. The most conservative explanation came from the past itself. Einstein's abandoned cosmological constant, once discarded as a mistake, returned with new life. Perhaps space itself carried energy, an intrinsic property of the vacuum. Empty space would not be empty at all, but suffused with a faint, uniform density that never changed. This vacuum energy would act as a repulsive pressure, pushing galaxies apart while remaining constant across time. The elegance of this model was its simplicity. A single number, lambda, added to Einstein's equations, could explain acceleration. But elegance hides a wound. Quantum physics predicts vacuum energy too, but in quantities so immense that the universe should have been torn apart long ago. The fact that the observed value was not 10 times greater, but delicately small, seemed almost absurd. It was as if nature had tuned the dials of existence with infinite precision, leaving physicists to wonder why. Some accepted the cosmological constant as reality, a brute fact of existence, no more explainable than the speed of light or the charge of an electron. Others recoiled, refusing to surrender the search for a deeper cause. From this refusal emerged another vision. What if dark energy was not a fixed property, but something dynamic, a new kind of field, spreading through space, evolving with time? Scientists called it quintessence, borrowing a word from ancient philosophy, the fifth essence, beyond earth, water, air, and fire. In this model, dark energy is like an invisible ocean, its waves rising and falling across cosmic history. Today, it drives acceleration. In the past, it may have been weaker. In the future, it might change again. Such a field could vary its strength, opening the door to cosmic destinies not yet written. Perhaps expansion would one day slow. Perhaps acceleration might reverse, collapsing the universe into a final crunch. Quintessence offered a hope that dark energy might not be eternal, that it could be studied through its evolution, but it also carried danger. If the field shifted unpredictably, the universe's fate could be far stranger than a slow fade into silence. A darker speculation soon emerged. If the pressure of dark energy were even stronger than a cosmological constant, then acceleration would not simply continue, it would escalate. Galaxies would recede, not just steadily, but violently. The expansion would grow so fierce that eventually it would overwhelm gravity. Then stars, then planets, then molecules themselves. At the end, even atoms would be torn apart. This apocalyptic scenario is known as the Big Rip, a vision of the cosmos not ending in cold emptiness, but in catastrophic dismemberment. Though it lies billions of years ahead, it lies at all the very possibility shifts the meaning of dark energy. It is not simply a silent background, but a potential destroyer of worlds. For now, evidence does not demand such extremity, but the mathematics allows it, and the thought lingers like a shadow. The universe may not merely fade, but fracture. Others questioned whether dark energy existed at all. Perhaps the acceleration was not caused by a new form of energy, but by gravity itself behaving differently on cosmic scales. Einstein's general relativity had been tested in solar systems, in galaxies, in black holes. But could it fail across billions of light years? Modified gravity theories attempted to rewrite the laws themselves. Some proposed extra dimensions, hidden from perception but altering cosmic expansion. Others suggested that gravity weakens over vast distances, unable to bind galaxies as expected. In these models, acceleration is not driven by a force, but by a flaw in our understanding of spacetime. The allure of this idea is its audacity. To explain the unknown, one must dare to alter even the most sacred equations. Yet each test so far, from gravitational lensing to galaxy clustering, has reinforced Einstein's framework. If relativity is broken, it hides its fractures well. And then there are explanations that reach beyond science into philosophy. If quantum theory and inflation suggest the possibility of multiple universes, each with different laws and constants, then perhaps dark energy is not a universal truth, but a cosmic lottery. In this view, countless universes exist, some with immense vacuum energy, others with none at all. Most would be sterile, unable to form stars or galaxies. Only in rare cases would dark energy be small enough to allow cosmic structure, and in those rare cases, beings like us could evolve to notice it. This idea is known as the anthropic principle. We observe dark energy to be finely balanced because only in such a universe could we exist at all. It is an explanation not of mechanism, but of inevitability. Yet it leaves many uneasy. For some, it feels less like science and more like surrender. An acceptance that deeper understanding may be forever out of reach. Still, imagination pushes further. Could dark energy be a hint of hidden particles, ghostly quanta, yet undiscovered? Could it be the imprint of higher dimensional brains, rippling in ways invisible to three-dimensional beings? Could it be the residue of a false vacuum, a metastable state destined to collapse in a cataclysmic phase transition? If so, the universe may not be eternal at all, but balanced precariously on a temporary plateau of stability. One day, without warning, the false vacuum could decay, rewriting the laws of physics in an instant. A silent apocalypse, spreading at the speed of light, leaving no trace of the universe that came before. Such speculations may seem like science fiction, yet they arise from the mathematics of quantum fields and cosmology itself. The universe offers no promise that its stability is permanent. What unites all these theories: cosmological constant, quintessence, phantom energy, modified gravity, multiverse speculations, not certainty, but longing. Each is an attempt to place a frame around the unframeable, to translate the silence of dark energy into human understanding. But none has yet succeeded. In the laboratories of Earth, dark energy cannot be bottled or weighed. In the equations of physics, it remains slippery, resisting clarity. In the night sky, it appears only as an absence, a subtraction from what should have been. And so, humanity is left with visions of possibility. A universe that fades into darkness. A universe that collapses in fire. A universe that rips itself apart. A universe that was always one among many. Each possibility is vast. Each is terrifying. And each leaves behind the same haunting question. Is dark energy a property of reality itself? Or simply the shadow of something greater? Theories and speculations offer maps, but the territory remains hidden. The silent force continues its work, carrying galaxies outward, stretching the void, rewriting destiny. And science, for all its brilliance, can only stand at the edge, sketching possibilities into the unknown. The mystery of dark energy, vast and impenetrable, cannot be solved with thought alone. It demands tools, eyes sharper than human vision, instruments more patient than human lifetimes. Machines capable of listening to the whispers of the cosmos across billions of years, to pursue the silent force that drives galaxies apart. Science has built an arsenal of devices scattered across deserts, mountaintops, and the void of space. Each one is a fragment of humanity's determination to illuminate the unseen. Every telescope is a machine that looks not only into space, but into time. Light from distant galaxies carries history, crossing billions of years to reach us. By measuring it, astronomers reconstruct the unfolding story of cosmic expansion. The discovery of dark energy itself was born of this approach, using the steady brilliance of type Ia supernova as cosmic mile markers. But the deeper the questions grew, the more precise the tools had to become. The Hubble Space Telescope, orbiting above Earth's atmosphere since 1990, became one of the first great soldiers in this quest. Hubble's clarity allowed astronomers to capture the faint signatures of supernova, so distant that their light had been traveling since the universe was less than half its present age. With each flicker recorded, the evidence for acceleration grew harder to ignore. Hubble transformed abstract theory into measured fact. Yet supernova were only one part of the puzzle. To test the universe more completely, scientists turned to the cosmic microwave background, the ancient afterglow of the Big Bang. Satellites such as WMAP and later the Planck Observatory mapped this radiation in extraordinary detail, revealing subtle ripples in temperature across the sky. Those ripples carried the blueprint of cosmic structure, encoding the density of matter, radiation, and the elusive dark energy. The results were startling. Planck's precision confirmed that nearly 70% of the universe's contents had nothing to do with atoms or dark matter. Dark energy was everywhere, smooth and uniform, its pressure shaping expansion on the grandest scales. The cosmos itself bore the imprint of a force no one could see. The investigation moved beyond single points of light to the vast architecture of the universe itself. Large-scale galaxy surveys, like the Sloan Digital Sky Survey, mapped millions of galaxies, tracing the cosmic web that stretches across the sky. Within this web lay a subtle signature known as baryon, acoustic oscillations, faint echoes of sound waves that rippled through the early universe. These echoes acted like a standard ruler, their size fixed at the dawn of time. By measuring how far apart galaxies were across billions of years, cosmologists could trace how space itself had stretched. The rulers showed the same truth. The universe was accelerating, and dark energy was its silent architect. But still, the data were not enough. Was dark energy constant or dynamic? Was it truly vacuum energy, or something stranger? To answer these questions, science entered a new era of instruments built not just to observe the universe, but to hunt this one enigma directly. The Dark Energy Survey, launched in 2013, scanned the southern skies with the Blanco telescope in Chile, measuring the shapes of hundreds of millions of galaxies. By studying their distortions through gravitational lensing, it mapped the invisible scaffolding of matter and the influence of dark energy upon it. In 2021, the Dark Energy Spectroscopic Instrument DESI began its mission, aiming to record the spectra of over 35 million galaxies and quasars. Each spectrum, with its delicate shifts in wavelength, became a data point in the expanding map of the cosmos. DESI's goal was nothing less than to chart the universe's history of expansion with unprecedented precision. And beyond Earth, new missions were launched. The European Space Agency's Euclid spacecraft, launched in 2023, now maps billions of galaxies across more than a third of the sky, searching for distortions and patterns that betray the fingerprints of dark energy. NASA's Nancy Grace Roman Space Telescope, set to follow, promises to extend the legacy of Hubble with instruments designed to probe cosmic acceleration directly. These missions are more than machines. They are expressions of humanity's refusal to accept ignorance. They stare into the abyss of time and space, gathering the faintest signals to confront the greatest silence. All these tools converge on one elusive goal: to measure the nature of dark energy through a single parameter, known as W. In physics, W describes the ratio between pressure and energy density. If dark energy is a cosmological constant, W should equal -1. If it is quintessence, W may vary. If it is phantom energy, W falls below -1, heralding a universe that ends in rupture. Every telescope, every survey, every spectrum is, in some sense, an attempt to pin down this number. To measure it, not just once, but across time, to see whether dark energy is truly fixed or evolves with the cosmos. The answer will decide the universe's fate. Yet so far, the results hover tantalizingly close to -1, neither confirming nor ruling out other possibilities. It is as if the universe is teasing, allowing glimpses of possibility, but never clarity, whispering truths that dissolve as instruments sharpen their gaze. Some scientists have dreamed of detecting dark energy not across galaxies, but in laboratories on Earth. Could delicate experiments, using ultra-sensitive detectors, measure the faintest forces of the vacuum? Could particle accelerators, like CERN's Large Hadron Collider, produce hints of the fields that drive cosmic expansion? So far, no laboratory has succeeded. Dark energy remains aloof, untouched by direct experiment, revealing itself only in the grand theater of the universe itself. Yet the search continues. Proposals emerge for new detectors, new methods, new collisions of particles. The hope is that one day, the same equations that explain atoms and quarks might also explain the force stretching galaxies apart. But the deeper the tools probe, the more contradictions emerge. The Hubble constant, the measure of how fast the universe is expanding today, refuses to settle. Observations from supernova give one value. Measurements from the cosmic microwave background give another. The difference is small in percentage, but vast in implication. If the numbers cannot be reconciled, then perhaps dark energy itself is evolving. Or perhaps physics itself requires rewriting. This tension has become one of the most urgent frontiers of science. Entire missions are dedicated to resolving it. Yet as the data improve, the contradiction does not fade. It sharpens, as though the universe is pulling scientists deeper into its labyrinth. The search for dark energy is not the work of a single nation or institution. It is a collective endeavor, spanning continents and generations. On mountaintops in Chile, Hawaii, and the Canary Islands, telescopes scan the sky. In deserts and labs, detectors hum quietly. In orbit, satellites sweep the heavens with unblinking eyes. Thousands of scientists share data, refine models, and argue over interpretations. And yet, despite this vast machinery, dark energy remains untouchable. It leaves no particle track, no spectrum line, no glow of radiation. It reveals itself only through the grand choreography of galaxies drifting apart. The search is not over. In truth, it has barely begun. Each mission extends the map, each observation sharpens the picture, but the final portrait is incomplete. Dark energy remains as it was first glimpsed, an invisible presence, revealed only by absence, defined only by the motion it compels. Perhaps the answer lies in tomorrow's data. Perhaps in a new telescope not yet built, a new equation not yet written, a new insight waiting in the mind of someone not yet born. Or perhaps dark energy is a truth forever beyond measure, woven into the foundations of reality, untouchable by human hands. But for now, science continues. The telescopes turn, the satellites scan, the data flow. Humanity stares into the abyss, armed with instruments of glass and steel, listening for the faintest echo of the force that shapes all things. In the end, dark energy is not only a scientific mystery, it is a mirror held up to existence itself. The galaxies flee from one another, carried on currents we cannot see, accelerated by a silence we cannot name. The numbers are precise, the measurements are clear, but the meaning lies beyond the reach of certainty. And in that space between fact and understanding, humanity is forced into reflection. For most of human history, the night sky was thought eternal. Stars wheeled overhead in patterns fixed and unchanging. The cosmos was a backdrop for life on Earth, not a story of its own, but science has stripped away that illusion. The stars are not eternal. The galaxies are not fixed. Even the universe itself is not steady. Everything is moving, rushing outward, compelled by a force that remains forever hidden. What does it mean to live in such a universe? A universe in which the familiar, the atoms of flesh, the orbits of planets, the clustering of galaxies accounts for less than 5% of reality. A universe in which the dominant force is not matter, not light, not even gravity, but a nameless presence that offers no explanation of itself. Philosophically, the discovery of dark energy is an act of humility. It reminds us that knowledge, however vast, is fragile. At the turn of the 20th century, many physicists believed the great questions of science were nearly solved. Then relativity, quantum mechanics, and the expanding universe arrived. At the end of the 20th, the discovery of dark energy overturned certainty once more. The cosmos reminds us that just when the story seems complete, the plot twists, and the mystery deepens. Dark energy also forces reflection on destiny. For centuries, humanity has wondered how the world might end. But now the question expands. How will the universe end? If dark energy is constant, then the future is a slow fading. Stars will burn out, galaxies will drift beyond sight. The night sky will empty, and time will stretch toward heat, death and infinite silence, after all fires have gone dark. If dark energy is phantom, the future is violent. A universe torn apart, atom by atom, space-time itself shredded in the Big Rip. If it evolves, other fates may await a collapse back into fire, or transformations we cannot imagine. Whichever path is true, the meaning is the same. Humanity exists in a cosmos whose fate is determined not by what is seen, but by what is unseen. Every life, every thought, every civilization unfolds under the dominion of a force that neither senses nor instruments can grasp. And yet, within this unsettling truth lies something profound, that we can even ask the question, that creatures of dust and water, on a small planet orbiting an ordinary star, can measure the faint light of ancient explosions, trace the pattern of galaxies, and glimpse the destiny of the universe itself. Dark energy may remind us of ignorance, but it also reveals the astonishing capacity of human curiosity. We may not yet understand the silent force, but we have seen its shadow. We have named it. We have begun the search. There is a kind of poetry in this. The galaxies may rush away, but for a moment in cosmic time, humanity is here to witness them. The sky above us is filled with stars precisely because dark energy is balanced so delicately. Too strong, and galaxies would never have formed. Too weak, and the universe might have collapsed long before life could arise. Whatever its true nature, dark energy allowed existence as we know it. Its silence carries not only mystery, but also the improbable gift of being. Perhaps this is the deeper meaning of the discovery, that reality is not only stranger than we imagined, but more fragile. That existence itself rests upon a balance we do not understand. That the silence pulling galaxies apart is the same silence that allowed them to form, and with them, us. And so, dark energy becomes more than a scientific puzzle. It becomes a reminder of perspective, a reminder that our stories, our histories, our struggles, unfold in a universe vast beyond comprehension. A reminder that certainty is temporary, but wonder is eternal. A reminder that even in ignorance, beauty endures. In the coming decades, new telescopes will rise. New missions will launch. New equations will be written. Perhaps they will bring clarity. Perhaps they will only deepen the mystery. But either way, the universe continues. Galaxies recede. Space expands. The silent force carries all things outward. And humanity, for a brief, luminous instant, stands awake beneath the stars, aware of its smallness, aware of its wonder, aware of the silence that rules the cosmos. The mystery remains unresolved. But perhaps resolution was never the point. Perhaps the meaning lies in the search itself, in the act of turning eyes to the sky, of building instruments to measure the unmeasurable, of daring to ask questions whose answers may never come. For in that act, the universe speaks to itself through us. Consciousness emerges from stardust, gazes outward, and discovers the currents of the infinite. Dark energy pulls galaxies apart, but in its mystery, it pulls us inward to reflection, to humility, to awe. The silent force continues. The galaxies drift away. And the universe, in all its vastness, remains both unknowable and beautiful.